homework 5 and 6 presentation. So from homework 5, we need to show proof for the shear modulus. Um, so basically, how I did this was I showed just like the general shear for a square, A, B, C, D, and I showed it as being shifted to the left due to the shear stress. From there, you can probably, oh, good lord, okay. Sorry about that. From there, you can see that that there are two different normal stresses occurring within within the square. So one is like a compressive force, one is a tensile force, and that would be equal to that shear stress. From there, you can calculate the shifting from the tensile strain across BD by adding up the um, uh, the shear stress over the uh, Young's modulus, which is basically Hooke's law. So by adding those up, you can see that this is going to equal to like shear stress over Young's modulus times shear stress over Young's modulus times 1 plus the Poisson's ratio. From there, basically what I did, I calculated the shear strain that occurs basically like from this shifting from D to D1. So the shear strain can be seen by D1 over AD, those lengths. Because, yeah. So from there, you can look at the tensile strain across BD in a different way as well. So you can look at it in terms of these lengths that are being elongated, due to the shear stress, and from there we end up calculating that the BD or the tensile strain across BD would equal to approximately 1/2 times the shear strain. So by equating these two equations together, you end up getting, you can end up solving for G. Well, you end up getting one half over you end up getting 1/2 over tau over gamma, or over G, and that can be rearranged to find this particular version of the shear modulus.
So for the C44 value in the stress matrix, we have to set up a couple of like the primary structural equations. We have Young's modulus, shear modulus, Poisson, and then the elongation is just a reworking of the Poisson. I use notation, then the others I did, is that sigma, or is that the one with the 3, or is that lowercase?
Oh, that's epsilon.
That's epsilon, yeah. But it still is the lateral and longitudinal strain. And yeah, based on this we have, which was proved in the last slide, the shear modulus formula. And then just based on the requirements of the material itself, and because it has I think for this one it was supposed to be elliptical, so it has two axes of symmetry. We can just go straight to substituting in C44 for the Young's modulus. And the relationship between C44 and C22 and 23 is C22 minus C23 over 2.
How do you come up with the final result?
I found something online that was.
This is for composites, right? So
Yeah.
you cannot use your isotropic relationships.
Oh, okay. I don't know. I found something and it said that, because for elliptical ones, it said that because of two axes of symmetry, you can jump straight to C44, but I don't know if it was specified for composites or not.
No, it has to go along very similar lines to what Nilesh presented. Just that you have to take the appropriate C coefficients instead of the J E's that she was dealing with. So I think, is this all that you have for this particular problem?
For this one, yeah.
I would like you to read this next week. So you go through a very similar procedure that was presented so that you can, you cannot use these G's, E's and U's without subscripts and the appropriate subscripts that is. So, but the principles, the physical principles are very similar, just that it's a little more complicated than what was presented for the isotropic. Just try to take a look at that.
Okay.
Might be able to see this proof in some books as well. I don't mind you taking it from there, but important to walk us through all these steps involved before we get there.
Okay.
Okay, so this was the variable chart we were able to come up with. So for our loads, we added various forces that we didn't mention in class. So thermal forces, viscal forces, electrostatic and magnetic forces. We also added types of loading, so monotonic, where it's just sort of extended, a specimen might be extended only once, whereas in cyclic extended maybe 2 or 3 times, and it's loaded and unloaded multiple times. And then we added the discontinuity for the equilibrium equations. That would be like the natural sort of discontinuity. For stresses, we added transverse shear, longitudinal shear. We also added viscous stress, which correlates to the viscous force. And we also added true and engineering stress, which can be computed from various Young's modulus values. And we also added tensile and compressive stresses to that. For viscosity, for constitutive laws, we added viscosity and work to the list. And then for strains, we added shear strain as well as strain rate, which relates to the viscous stress equaling the viscosity multiplied by the strain rate. And then we also added the Lagrangian finite stressed strain tensor, which is which sort of includes higher order terms for large deformations. And then we also just included, since velocity and acceleration were included in strains, we included further derivatives. So the fourth derivative position, jerk, and the fifth derivative with snap. We can obviously go further with that. For kinematic equations, we included the polar moment of inertia, not to be confused with mass moment of inertia. We included thickness as well, which is sort of goes in line with the geometric parameters. We also added curvature, which is, like as it says, one over the radius of your specimen. And we also added geometric discontinuity. And then for the deformations, we added thermal expansion or compression, which correlates obviously to the thermal force. plastic deformation, so the opposite of elastic deformation. Viscous deformation, again correlating to viscous force, electrostatic deflection, electrostatic force, and magnetic deflection as well, which correlates to the magnetic force. You want to take this?
So to compare GJ for the thin-walled rectangular beam and the solid rectangular beam, first, assuming that the beams are made out of the same material, the shear modulus is going to be the same since it's a material property. As far as the polar moment of inertia, that's a geometric property, so that's going to differ between the two. So by adding the moment of inertia with respect to the x-axis to the moment of inertia with respect to the y-axis, we found the polar moment of inertia of each beam. And so by dividing the thin-walled beam by the solid-walled beam, we found like a relation between the two. And that relation is basically the thin-walled beam can be modeled by 4t, which is the thickness, times a plus b, the length plus the width, divided by a squared plus b squared, which would be the length squared plus the width squared. And so if you have a very large thickness relative to the length and width, then the thin-walled beam will have a higher shear modulus times polar moment. Whereas if you have a larger width and length with respect to the thickness, the solid beam will have a larger polar moment value.
While the derivation is okay, I just want you to be a little more precise in terms of the name you use for J. J is happens to be equal to the polar moment of inertia only for circular cross sections, solid and hollow. Any other cross sections, including the rectangular, it is just called the torsional constant. Okay. J, and it can be very different from the polar moment of inertia. So the I's that you have used, none of them are, or the J for that matter, none of them are polar moments of inertia.
Okay.
Okay, so for the derivation of the shear stress over the normal stress max for both, for an elliptical cross section, we make the assumption that it's obviously thin-walled, and then even after deformation, the plane.
This is solid cross section, right? Not thin.
Yeah. Okay. Yeah. So, okay, then we make the assumption that even after deformation, it remains in plane, and also that our material follows Hooke's law. So we start with the general formula that the shear strain equals the torque multiplied by any radius divided by our torsional constant multiplied by our torsional shear modulus. From the elliptic cross-section, we can find that J is equal to pi multiplied by our semi-major axis multiplied by our semi-minor axis cubed over 4. And then to maximize our shear stress, we need to take the maximum radius, which is the semi-major axis. So then if we plug in A for R max, and also our formula that we found for J, we basically get that the shear stress max equals 4 times our torque divided by our shear modulus multiplied by pi multiplied by our semi-minor axis cubed. And then a similar sort of formula for our normal stress. We found that our I would equal pi multiplied by A multiplied by B cubed over 4. Again, to maximize our normal stress, we have to maximize which radius we use. So in that case, that would be y max, and it would be b. And so if we plug that in for y max, and we plug our formula we found for I, we find that the normal stress max equals 4 times our torque divided by pi ab squared. And then just taking tau max and dividing it by our normal stress max, we get the following relation. We can divide and cancel out our b squared term and also our pi term. And so we end up with the shear stress max over the normal stress max equals A over G times B.
There's something wrong there because it's a ratio of stresses, right? It should be a non-dimensional quantity, whereas A by B is a non-dimensional quantity, but G is having a dimension, right?
Right.
So something has gone wrong, and also not fully satisfied with derivation. I urge you to go from the first principles
Okay.
and redo this next week.
Okay.
So that first of all, the check is that it should be non-dimensional, but the other more important thing is in terms of starting from the very basics, like how we did for the circular cross section, and trying to derive those results, because you can't directly take the results from any other type of cross section, right? For an elliptical cross section based on the equation of the ellipse, it has to come from that, because there has to be an integration that is taking place over the cross section, and those integrations have to be explicitly shown to get your results.
Okay.
Okay, so for the derivation of tau max flange over the tau max web, we have to start out with saying that the maximum tau max flange is at the outer layer of the fiber, and the sigma max flange maximum is at the surface. So using that, we can use these assumptions to say that tau max web is at the axis, and the sigma max web is also at the surface. And we have to use the moment of the flange and the web, not the moment, the distributed load of the flange and the web to further our calculations. And same thing, setting up with the area of the flange, because this is a T-section beam. And for the E-flange, we get the E-flange is the area times the force over the E-web, and then that would simplify to the area times the applied load, or the distributed load. And the Vmax is just it's just the distributed load times the length over 2 to find the average. And here we can substitute in based on our original assumptions up there, that the Tmax flange is these long equations that I'm not going to say out loud, but they're right here. And same thing for the max flange. It's the same thing, just with different variables and different, instead of a force, it's now the applied load in this one. And to find the relationship between the two, you just divide, and that simplifies out to being the area times the applied load times B times W over AF times BF. And then here you can see some of the points on the surface that were used to create the assumption.
Some of the comments that I gave earlier goes for this as well, because we have to go from the first principles. So you will have an equation which is for the rectangular cross section. We showed that it's essentially a parabolic distribution, and parabolic should have a square term in the vertical coordinate. So whatever vertical coordinate you're using for that, and then you have to maximize that particular equation. So here it's no not very different from that. It's just that instead of one rectangular cross section, you have two rectangular cross sections which are put one over the other, of different dimensions, of course. And so then from there you go in a piecewise parabolic equation for that, and from that you have to actually take the derivative to get to set it to 0 and then find the maximum. The typical way you use calculus to find the maximum of a polynomial. So I want you to go over the first principles there.
Okay, it's probably the same comments for this one too, because I just did the same thing and this time for Sigma Max Web. But here you can see the work that I did. Even though it's not parabolic, this is what I have so far.
It's an elliptic cross section.
Yeah, I wrote it. Oh no, that's not supposed to be there. Sorry.
Yeah. Okay. I expected something a little more because you had enough time as well. So in terms of previous, when this was handed out to now, so I really urge you to work on this, especially the chart on the variables. I expect something far more than that, because that's kind of a take-home findings. So you really want something much more concrete over there, rather than just listing out a few additional variables. In terms of like the examples that we do, and this is a class, by the way, I'm talking to him because he presented that, but remember that this is a team task, so all of you are responsible for that to contribute towards that. So while some of the things need to be reworked by you individuals, but I think for that I really want all four of you to put your heads together and spend quality time in trying to get to that chart in a similar way that like how we were explaining, remember, for a beam or for a torsional tube or for an axial bar, how we gave those variables and then we brought them together to get to those equations. And so I understand you're doing something very similar to what I was doing on the board, but that was an exercise just to get to that level. Okay, but now that that has been already presented to you, I want you to go from there where we left off in the class in terms of like, for example, we derived the equations for the stiffness and bending to be EI, to be EA in the case of the axial bar, GJ in the case of the torsional shaft, right? So how did we get there? It's by using all those four variables and set of equations in between, and use more imagination in terms of your presentation to make it more distinguishable between the four variables and the three equations. It looks like all of them are kind of very similar quantities. And the equations are also, you're putting things that the equation depends on rather than the equation itself. So you put the equation and then you talk about what all it depends on, which are the parameters you already listed. So I really want a much more comprehensive work on that. While of course a few of these things you have to rework, but that's a minor thing. Most of your time this week should be spent from now to next Thursday should be spent in trying to get to that chart in a much more useful manner, because there's a lot that goes into it in terms of an overall understanding of this problem. So it's very important that the takeaway is like a really good quality poster that you could probably even put up in your living space to give you a visual appreciation of the physics and maths which goes behind it. So once you do it, I tell you right now you may not be able to see it, but once you do it, you will see the real huge benefit of it. And I'm saying this not based on my own experience, as I said, a lot of other students have really immensely benefited from this. So I really want you to take that as one of the biggest takeaways from this whole course.
So for the final project, it's not like an individual like type of assignment, right? It's like we're all working together and we're all
Exactly,
presenting
exactly.
closer
So
together.
maybe immediately after this class, you four can meet together
Yeah.
to decide on how you want to segregate the responsibilities so that all of you pour into it, essentially, right? And so it has to be far more comprehensive. So since four of you are there, it makes it even more easier to feed in the information. But the structure is very important, that you get the big picture in your mind. And then you see where all the things that you have learned exactly fit in. Okay. I'm glad you brought in a lot of things like jerk and snap and higher order derivatives and things like that. That's nice, cute. But I want it to be much more practically useful. So that's what, which means that you actually get into the nitty-gritty, the details of the equations, the way we present it for bending, for torsion, and for the axial elongation. So something on those lines, but for many more problems, and trying to see how all of these, see, the whole idea, as I said always, is to connect the load and the deformation. And then it's very difficult to directly connect them. You bring in these intermediate quantities and then the equations which relate them, and then you try to get to that. Okay. Sorry if I sound harsh, but I just only want it to be of greater benefit to you. So that's the only reason why I would urge you to redo it in a much better way than what was presented today.
Yeah, I personally didn't realize like that's what we had to do for today's
Yeah.
assignment. You know.
Did you read that one-page explanation that I gave? The homework document. It was there on Teams.
Yes.
So
Yeah.
I think it was very clear as to what
Yeah.
is anticipated. So
Okay.
okay.
Okay, I think I understand.
So anyway, it
now,
doesn't
so,
matter.
yeah.
So what's done is done, but
Mhm.
the focus has to